Hello, my name is Valerie Stolf and I will be reporting my results and observations for Physics 2212, Lab 5, Magnetic Braking with Faraday's Law. The purpose of this lab was to predict the motion and magnetic interaction of a magnet falling through a conducting tube. Faraday's law was used to be able to predict the magnetic flux when the magnet is at different locations in order to predict the current in the tube at these locations. The Biot-Savart law was used to calculate the force on each ring of current throughout the tube, and Newton's second and third laws were used to measure the forces acting on the magnet in order to predict its motion. Overall, I found that when performing the experiment, the magnet took a total of 1.28 seconds to fall through the tube. However, the VPython simulation indicated that the magnet would take 0.24 seconds to fall through the tube. In performing the experiment, the tube was created by folding common household aluminum foil. The tube had a length of 0.32 meters, the width of the foil was about 0.0024 meters, and the inner and outer radii of the tube were respectively 0.0245 meters and 0.0243 meters. The magnetic moment found in Lab 3 was used in these calculations at a value of 1.89. In this experiment, the magnet was in the tube for 1.28 seconds. I compared this measurement with the magnet falling at the same length in free air, and the time to fall was found to be 0.224 seconds. It was then observed that the magnet falls slower in the metal tube and falls faster when falling through free air. For my VPython computational model, I first initialized the measurements in my aluminum tube and relevant constants shown in the left image. Then in the right image, the tube is created and also its parameters are created. This will show the simulation of the magnet falling through the tube. The next code snippet creates a magnetic field and magnetic flux, seen specifically in lines 88 and 101 and 102. This part of the code creates the motion of the magnet through the metal tube. This includes calculations for the force of gravity, the magnetic flux, and for finding the current through the tube. This code segment focuses on the current and magnetic field in the rings in the tube. It also updates the magnet's motion through the tube. Here to the left, we see two rings at a location as they fall through the tube. The simulation showed that at time equals 0, there are no rings in the tube, but as time continues, two rings appear at the top and begin to fall through the tube until the magnet exits the tube and the rings disappear. Since the magnet is falling down through the tube and the rings are blue, then the magnetic flux also increases in the downward direction, and therefore the blue color indicates a counterclockwise current. If the rings were red, this would indicate that the current was clockwise. Theoretically, the magnet should have reached a terminal velocity and shown a curve, seen in the right image, that becomes more horizontal over time. This error is likely due to discrepancies with the actual magnetic moment, and my value of 1.89 was used in this experiment. This is also why the magnet is shown to be in the tube for only 0.24 seconds instead of for a longer time as expected. I did find through editing the mu value in my model that when the moment was increased, the model showed results that were more in line with what was expected. To conclude, if the resistivity of the conducting tube was actually very close to 0, then the induced current would increase in accordance with Ohm's law. Because of this, the magnet would fall at a slower speed. Furthermore, if the aluminum tube was filled with holes throughout, the magnet would fall even faster through the tube because the magnetic force would be of a lower magnitude. Because of this, the induced magnetic field would also have a lower magnitude, so the magnet's speed would not be slowed to the same extent. Thank you for watching.